In this video, we learn to integrate, differentiate inverse trig functions. Inverse trig functions are introduced, defined in trig. Let's just quickly recall how it's done. Start with the sine trig function, one of the 6 trig functions. Algebraically, we define inverse of any function as the following: switch x and y. Mathematically, we have an equation with the x and the y variables involved. Suppose there is an input x here. Theoretically, there is a corresponding y value defined. This way, we consider such defined function y as inverse of sine, denoted as inverse sine. Sometimes it's called arc sine too. Either one is fine. This is more popular. It's simpler notation I use all the time. I'm lazy. Anyway, so this is how we define inverse sine algebraically. So you write the definition. So what's inverse sine of x? If x equal to sine y, then we say y is the inverse sine value of x. Now, geometrically, we can discuss the graph. Let's see. So sine looks like this. In geometry, if we flip this graph, about this dotted line, so we have kind of highlight a little bit so you see this is a reflection of sine about y equal to x, straight line. So generally in geometry, this is how we obtain the graph of inverse of a function. So this is a sine, this would be graph of inverse sine. With one problem though. In mathematics, any function must be single valued. So if we use the vertical line test to check out this graph, it doesn't define a function because, say we do a vertical line here, we're going to hit a lot of points. So just simple reflection of a sine will not give us the graph of inverse sine, because this graph doesn't define the function. First problem. What we do is to, in geometry, no, sorry, in trigonometry. So what we do is to only take this section as the graph of inverse sine. Now this time we have no problem whatsoever. You know, anywhere we draw a vertical line, do the vertical line test. The most we hit at one point, the red curve, or we had no point. That's fine. Just means, you know, such point is not in the domain of this inverse sine function. Remember, this is the refraction of sine, so we can accordingly figure out the domain. And range. Now we have a well-defined function, inverse sine, domain, -1 to 1, range, -π/2, 2π/2. It's important to know this kind of information, domain, particularly the kind of a value we can plug in here. So this expression is defined at all. It makes sense. Let's say from the graph we can see the domain is -1 to 1. In other words, any point outside it's not in the domain, like +2 or -1.5 or -10. Cannot plug in and evaluate, and it makes sense. Look at here. X is supposed to be the sine value, some sine value. Sine is never more than 1 or less than -1. Alright, so it makes sense algebraically and graphically too. So this be how we define inverse of sine. Now similarly, we can define inverse cosine, inverse tangent, inverse cotangent, inverse secant, inverse cosecant. And here, this is a calculus, so we're not going to go over all this trig stuff. I do have kind of a summary here. It's kind of simple, summary. So inverse sine, like I just showed, domain is -1 to 1, range is -π/2. There's inverse cosine, inverse tangent, inverse cotangent, and inverse secant, inverse cosecant. But I don't have it here. It's not important. What's important for us is to know how to differentiate these new functions, how to integrate problems involving inverse trig. Okay, here is the new differentiation formulas we have for inverse trig functions. Derivative of inverse sine is 1 over square root of 1 minus x squared. Derivative of inverse cosine is almost like that, with the difference is negative sign there. Derivative of inverse tangent, 1 over 1 plus x squared. Derivative of inverse cotangent, okay, difference is factor -1. Inverse secant, square root of x times square root of absolute value of x times square root of x squared minus 1, just to indicate that this has to be positive. When we do integration problems, differentiation problems, we usually don't have absolute value signs, but it's assumed it has to be positive. If it's not positive, we put absolute value there. Similarly, inverse cosecant, differentiated equal to negative. So in a way, you can see kind of paired up. So these are the 6 new differentiation formulas we have in this section. Now, more often, the expressions we see are not simply just plane x in, for example, inverse sine expression or in inverse cotangent. Usually it's more complicated. Okay, if it's just simply x, of course we use the formula, but what do we do if it's like a u, some expression u, which could be any function of x? What do we do? Well, it's pretty simple actually. What we see here is actually a composite structure, so like a composite function. There's an outer function inverse sine, there's an inner function u. So what we do is basically apply chain rule. We differentiate the outer to get, according to the formula here, 1 over square root of 1 minus u squared, and we differentiate the inner. So I call this as the general version or u version, which actually is more useful because we see expression instead of a plain variable x a lot. Alright, so no big deal. Just remember, it's really just matter of chain rule. You can apply this u version. Just remember, when you apply formula, it's 1 minus u squared, whatever u you have here, u squared and u prime. Okay, so you can similarly come up with the u version for each of the other 5 formulas, like this one. Just show you another. Secant u prime. So you're going to have u in place of x, u squared minus 1 u prime. Okay, this is just simply chain rule. We are familiar with the chain rule, so it doesn't matter you want to remember the u version or even the basic version. Basic version is fine. You want to do the u version is okay too. So these are the new differentiation formulas we learned in calculus. There aren't too many really differentiation formulas. Trig, inverse trig, plus very few basic ones. Power, exponential, log. That's it. Alright, so let's see some examples. Alright, first example, you can find derivative of y, which is log of something. Well, there's an inverse trig involved. That's why we're doing this problem here. Okay, like any problem we do, first thing we need to figure out is the structure of the function, so we know what rule to apply. Definitely we're going to apply the new formula, because there's an inverse trig involved, inverse tangent involved. So overall, what's this? It's composite function. It's a log of something. So first we're going to apply log rule. You can call log rule. We had log f prime equal to 1 over f prime. You can call log rule or chain rule, with the log being the outer, this thing being the inner. So either way, we can have 1 over the stuff inside, general logarithmic rule, 1 over the expression inside. So 1 over inverse tangent times, now just set it up right as a prime. So I'm not in a rush to try to get the answer in one step. This is just showing chain rule or logarithmic rule. I'll worry about this part later. Okay, so now differentiate this new function we are discussing in this section. Derivative of inverse tangent, well, is 1 over x squared. It's a simple x in there, so we use the basic version. Alright. Next, let's see how to differentiate y equal to arc sine tangent. Now, I usually don't use this notation. You see them, from time to time. So let's just see, what's arc sine? Arc sine is just inverse sine. It's the same as the inverse sine. So you can rewrite if you want. Okay. Now again, we want to find the derivative of this function. What kind of function is this? The structure. It's basically a composite function. Outer function is inverse sine, inner function is tangent. So you can consider it as a composite, or you can just consider it as the U version. You have inverse sine with something inside, tangent inside. Okay, so you apply chain rule or apply the U version of inverse sine differentiation formula. Either way, it's fine. So let's differentiate. Let's do the U version. Okay, I have it here. So first, we're going to have 1 over square root of 1 minus u squared. Now this is u, so we're going to have tangent x squared times u prime tangent prime. Now this is just to, again, in the first step, set up the expression according to the formula. Remember, have the u square u prime. Next, we take care of the detail, the leftover derivative of tangent. Well, this is nothing new. Derivative of tangent is secant squared. Now, all right, let's see one more differentiation problem. This time I'm going to find the derivative of power of some expression. Pretty complicated, pretty ugly. And let's just take time to know what's involved here. Okay, this function overall is a composite function. It's some stuff raised to negative second power. So we have this stuff, whatever that is. We don't need to worry about that in the beginning. So we have this stuff raised to power. It's a composite function. The outer function is power, inner function is this guy. So we apply chain rule first. Bring the negative 2 down, subtract the 1 from it, and copy down the inner function. Prime. Alright, so this is just simply chain rule. We have some expression reached the power. So we differentiate power, and we differentiate this inner structure in the back. Second step, we focused on the derivative of this inner function. So again, let's see what do we have. We have, actually, think about it, is this is another composite. or you can say the u version of inverse sine. Again, it's a coincidence. Look at the u version of inverse sine up here, and u version of inverse sine down here too. So we're going to use this formula again. The derivative of inverse sine, u version, is 1 over square root 1 minus, this is like the u now, u square times the u prime. This expression is not that complicated. We could have just get the 4x here, but I would rather show you the detail so you know what we have here, why we have this guy here. All right. Now we can finish up this problem. So it's 4x. Now the problem is done. Okay, so just like any differentiation problem, doesn't matter what it's like, how complicated it is, just take time, get focused on one thing at a time. This problem, the beginning, we treat it as just a composite, something reach the power, so use chain rule. And this part we handled in a separate step. Well, it's obviously involving inverse trig as outer, this as inner, so you can apply chain rule, or you can apply the u version of inverse sine formula. Alright. Now, since we got actually 2 out of 3 problems involving inverse sine, let's see one more. Just make up anything. Say have x squared inverse secant of log x. All right, this is a little more complicated. Let's see. Okay, what kind of function is this? It's a product. So we have of course, inverse trig too. There's a log inside the inverse trig, so that's detail structure. Overall, it's a product. So we're going to use product rule. Y prime product rule, very common, very important rule. We use pretty much all the time in differentiation problems. Again, like any differentiation problem I do, I always set up first. Product rule, derivative of the first term times the second factor plus first factor times derivative of the second factor, just so to show clearly product rule. Now continue to work on the details. Derivative of x squared is 2x. Second term, copy down x squared first. Then focus on this part. This part is obviously a composite structure. Outer function is the inverse secant, inner function log, or you can think of this as the u version of the secant formula, inverse secant formula here. Have stuff, not just a plain simple x. Some expression inside inverse, no big deal. You just do the u version, have the u in place of x, u in place of x, differentiate the x in the back. Okay, so the answer is 1 over, now you don't have to have absolute value signs, as long as it has to be positive for some x is negative, then you put the absolute value sign there. Okay, so you got the u in front of the radical. Under radical, you have the u squared minus 1 times u prime. Alright, so that's how we differentiate this factor. Copy the first term, finish up the second term. This fraction, there's no differentiation involved, so again just copy it down. The only thing we need to do is to differentiate log, which is 1 over x. If you want, you can simplify this a little bit. There's x squared, there's x, cross with x. You have x over log x. Alright? So done. So it doesn't matter, where you see the inverse in composite structure, in the product, in fraction, division, just apply whatever rule appropriate. When it comes to differentiate the inverse trig that we are actually learning in this section, just apply those rules. If it's a plain simple x variable, use the basic formulas. It's more complicated, it's some expression instead inside inverse trig. It's composite. You use general, or you use just as what I call it the U version. Now let's talk about integration involving inverse trig functions. Let's start with for example, inverse sine. Derivative of inverse sine is 1 over square root of 1 minus square. Now, if we integrate both sides, we would have a related integration formula. This is always true. From any differentiation formula, we end up with a related integration formula called antiderivative. Now, antiderivative is not unique, so you could always have c here, because if you differentiate both sides, the c is gone. You get that, right? So this way, we have one very important integration formula. Let's check what we have according to this differentiation formula. We would integrate again both sides. Oh, there's a negative sign there. So if we integrate both sides, we end up with say another formula. But if you compare this formula to that, they're not that much different. So from derivative of inverse cosine, we don't really need to try to come up with another formula. What we have is basically the same kind of expression to integrate, similar, not the same, with the negative sign. So this is not quite like a new formula. If you really want to say something, you say integral of 1 over square root 1 minus x squared dx equals negative inverse cosine with a constant, which is arbitrary constant. You don't need to put the plus c there. So you can see here from derivative inverse sine, we end up with the formula. From derivative inverse cosine, we end up with this, which is not necessary because we already have this formula for this kind of function to integrate, so it's not needed. For this reason, we're going to just keep this. So now similarly, we'll get two more integration formulas. This is the one I just discussed, which is based on derivative inverse sine. So from derivative inverse cosine, we won't get any new integration formula anyway, okay? Now from derivative inverse tangent, similar, we get this formula because, well, remember, derivative inverse tangent is 1 over 1 plus u squared. Derivative of inverse secant is 1 over u squared root u squared minus 1. So we get those two. And from derivative inverse cotangent, we will not get any new formula. So the same is with the inverse cosecant. From the differentiation formula, we will not get any new integration formula. Let's just keep the list. That's 3 formulas. Now it's these are the 3 new integration formulas we are learning. When we integrate similar structures, more often you see a number minus u squared, so may not be just simply 1. Rarely would you see 1 minus u squared or 1 plus u squared or u squared minus 1. It's better actually to become familiar with what I call the more general version of those formulas. So you have a number here, positive number, that's what I mean here. So a squared doesn't mean you're going to always say a perfect square, say 25 5 square or 9 3 square. Could be any positive number. Could be, say, square root of 7 minus u squared. So that can, of course, be considered as a squared. So your a is square root 7. That's simple to figure out anyway. Alright, now what happens is, if you have like a squared minus u squared, right, you can do algebra. You can factor out the a squared and then take it all the way out to the front of a square root or even the integral sign. You would end up with 1 minus u squared over a squared. So you would have your 1 here, like the 1 there. With a simple substitution, you figure that it would be this. Now, the general version of this formula with the a squared here, similarly, if you do the algebra, factor of the a squared, do substitution, you would end up with this. So it's algebra. So we don't really need to do that all the time. This reason, I'm giving you this more general formulas to use. Right. Before I show you examples, I want you to really kind of know these formulas, similarities, differences. Integration problems we do are naturally going to be mostly related to those formulas, right? So we need to know, which one to apply. Well, to know which one to apply, we need to know really more details of each. Like I said, similarities, differences. If you look at those three formulas, this one is a lot different than the other two because, well, there's no radical. That's one. Another thing is, between the variable and the number, the variable is square, always a square. It's plus. Well, the other two, you see minus, you see minus. So that's plus without square root. So what I'm saying is, if you see a function to integrate that doesn't have a square root, most likely you're going to use one of the first or third formula. All right. Also, if you see say no radical with a sum between two terms, most likely you're going to have to use this second formula. Now, with the radical, so you're going to choose between first and third. Now, which one? How first and the third are different? The main difference is the order of terms in the difference. Notice the first one is a number. A squared is a number. It's a number minus something involving variable. Well, the third one is some term, not necessarily square, you'll see, okay? Eventually, we would have to come up with a square in order to apply formula. Has to be always a square. And that can be done through substitution, and we do that a lot. So again, let's get back to the difference between the first and third. This is like a number minus stuff, or this is a stuff involving variable minus number. Alright, this is the main difference between first two. Okay, when we work on specific integration problems, we'll talk more about how we tell, how we determine which formula to apply based on all these observations, analysis. Alright, first let's see how to evaluate 1 over integral of 1 over square root of 16 minus x squared. So, well, first thing we see is there's a radical, square root. The square root, we're not going to consider formula number 2 because there's no square root. Also, it's a subtraction, 16 minus x squared, and this is sum, right? So clearly, we're not going to worry about the second formula at all. So it's between the first or the third. Now which one? First or third? Check the order of terms. It's a 16 minus x squared, number minus stuff, number minus expression involving variable. Actually, this is a square. That's nice. So we can apply this formula directly. Okay, this is order. Number minus. We decide to use the first one. Third one is expression minus a number. All right. So the first formula, it's straightforward. So 16 clearly, it's like a 4 square. So we get our answer according to the formula as a inverse sine x over 4 plus c. Very simple integral. Move on to next example. Okay, we have a fraction. One thing we notice, there's no square root. So there's no square root. Most of the time, you can pretty much forget about the first and the third. In math, we cannot say never. Alright, just most of the time. So we're going to try second formula. What's the second formula? Well, it's a fraction with the denominator being the sum of two things. One is number, other is better be a square, right? The other term better be a square. So let's check out what we have. We have on the bottom, there's something on the top. We're not going to focus on that. That's not our main concern. Also, what we can do with that later on. But to take care of the main issue. The main issue is that we have on the bottom sum of two things. That's kind of like that. The only thing is we have no problem with 25. 25 is 5 square. The only thing is this is not a square. We realize this formula is our only hope. So we better be able to use this formula. The formula here though has to be a square, u square. This is a 6 part. It's not a square. What do we do? Well, don't worry. This is very common. What we do is first force it to be a square. Rewrite it so it looks like a square. Rewriting. We do this all the time. So x to the 6th power, if you figure out the algebra, you would put the 3rd power there. Right? 3rd power reaches the 2nd power becomes 6th power. So what this suggests is we have to regard x to the 3rd power as u. Substitution. If x to the 3rd power is replaced by u, we would have the u squared plus 25, and we would be able to apply this formula if there's no other complication, meaning no other extra stuff that come with the substitution. Okay, let's see what we have through the substitution. Through this substitution, x to the 3rd power substituting u substituting x to the 3rd power. So this becomes a u squared plus 25. There's dx, there's x squared. Well, let's do our thing. So find the differentials on both sides. Well, it turns out perfectly x squared and the dx together is the same as 1/3. Just divide du. So this x squared is replaced by that along with the dx. This is perfect. This is what I was saying. There's no complication. You don't see for example use some other place or some x stuff left over. Alright, clean, simple, perfect new integral. It's perfect because it looks like just like this guy, number plus u squared. U squared plus a number, it's the same thing. So we apply formula. Formula says, well, you figure out the a, which is 5. 5 squared is 25. To be 1 over a inverse tangent u over a. 1 over 5 inverse tangent u over 5 plus c. And finally, we get our x to the 3rd power back for u. Done. Alright, so this problem shows that sometimes we need to rewrite in order to come up with the perfect square term. U square here, U square here, U square here. Very common. Let's see more examples. Okay, so we see in denominator x times the square root. There's square root. So that suggests that we better consider either the first formula with the square root or the third formula with the square root. Which one? Order of the terms. The first one is number minus expression involving x. Third one is expression involving x minus number. Look at what we have. We have expression involving x minus a number. So that says the third formula. Okay? The order of terms in the difference is what we check out. Not so much, whether there's stuff in the front. It's true, there's x in the front, but that's not the deciding factor. Deciding factor is the order of terms in the difference under square root sign. You cannot switch with the square root within square root. Okay. There are times you have square root stuff minus number even without stuff outside. If you do the for example appropriate substitution, you may end up with stuff in the front, so that you could actually also apply the formula. It's just because the order. Okay, so always check out the order of terms, whether it's a number minus expression or expression minus number. Number minus expression under square root, first formula. Expression involving variable minus number, most likely it's the third formula. Okay, so we're going to try to apply the third formula. Third formula, well, of course, we better have just square of a variable, new variable u. This is a sixth part of x, so we're going to rewrite. Actually, it's coincidence, the sixth part again. Anyway, it's an example that demonstrates, the process we go through, the thing we do in the process. So okay, we have a sixth part again. So our substitution again is x equal to u equal to x to the third power. So let's do the substitution. So the main structure becomes u squared minus 25. That's nice. What about dx? What about x? Well, let's work out on the side. We'll work on the side. Du equal to 3x squared dx. Alright. Now, what we need to get rid of in the integral is dx divided by x. So let's see what dx over x is. Well, for that we need to divide, first of all, both sides by x squared. And we need to get it over, right? And divided by x. So according to our differential identity here, dx over x would become that. Now it's good we have du, we must have du anyway. Now what are we going to do with this? Well, turns out it's perfect. The x times x to the third power is just u. 3, copy it down, first power, second power together is the third power. Third power is u. So this is just perfect. Not only can we get rid of a dx over x at the same time, we get also the u in the front that we really need. Without the u in the front, well, we wouldn't be able to apply the formula. Of course, it's not. This is not magic. It's designed to work out perfectly anyway. So okay, just by rewriting, introducing perfect substitution, we end up with this perfect integral again. So 1/3, 3 move up. What's left is just the third formula with a equal to 5. So we have 1/5 inverse secant of u/5 plus c. Alright, so simplify this again. It's 15. More important, get the third power of x in for u. Done. Okay, so many of those integration problems in this section involve rewriting and some sort of substitution you come up with after rewriting. Alright, let's see next problem. It's an integral of a fraction. What do we have? Well, this fraction, there's no radical, there's no square root, so we see, okay, we're not going to worry about the first or third formula. It's a sum, so every indication is that we'll probably have to use this formula. It's a sum, no radical, second formula. Second formula, you kind of try rewrite. You can rewrite x to the fourth power as a square to the second power. This next, you would consider u equal to x squared, and you go through the substitution, du equal to 2x dx. So with this substitution, you would have 1 plus u squared in the bottom, which is nice. What you get for dx is well, trouble, because there's actually a third power you need to get rid of, and through the differential, it's a first power here. So if you use a brute force to do the substitution, you will not get a clean 1/1 plus u squared du integral. There's something else there. Okay, so what it means is, well, this problem is not going to work out. If you do substitution, you will not be able to get inverse tangent formula to apply this second formula. We have this integration formula involving inverse tangent. Alright, well, this is math, you know. Sometimes, you know, you have some idea that seems to be reasonable. You try, it didn't work out. So turns out this problem is actually a very straightforward substitution problem. What we should do is a straightforward substitution. So just do u equal to 1 plus x to the fourth power. This way the bottom becomes u, that's the differential, 4x to the third power dx. So you see here this time, x to the third power is just perfect in front of dx. X to the third power dx. Same at 1/4 du. So 1/4 1/u just log u plus c. Integral of 1/u is log u 1/44. One plus f to the 4. All right. So this is just really like a curveball they throw at us. You expect, somehow this new formulas can be applied. It's true most of the time, but there could be exceptions. We should have to try. If it doesn't work out, try something else. That's what happened to this problem. So we didn't really even need this new integrating formulas to do it. Just keep that in mind. But mostly expect to apply these formulas, whether it's a direct application, number minus actual square, the pi formula get the answer, or more often you're going to have to rewrite a little bit, rewrite as a square, so you can try to apply the targeted formula. This formula is just very simple to figure out which one to apply. If you tend to apply one of those three, or try one of these three, first check, see if there's a radical in the denominator. With the radical, it's probably first or third. Without the radical, probably second. Okay. Without the radical, if it's a plus, of course you do that. Now with radical, then you decide which one to apply by checking the order, whether it's number minus expression involving x, or expression involving variable x or u minus a number minus term first, term involving variable minus number third. Just that simple. Alright, of course, don't be surprised that you cannot apply any of those formulas like this one. You just have to try to find out. Alright.